Hello everyone, this is the fifth lecture of week 5. So, in the previous lecture we looked at two variants of Newton's method. One is the damped Newton's method, which takes care of issues regarding no global convergence, and the other method is the modified Newton's method, which takes care of issues where minus h k inverse dk could be is not a descent direction, or it turns out to be a singular matrix, right. So, all of those issues can be rectified by either using damped Newton's method or modified Newton's method, right. So, we still have one more issue. Okay. So, let me point that out to you. Yeah. So, we took care of this no global convergence problem, we took care of this descent direction problem, we also took care of the singular h k problem. We still have this issue that matrix inversion is a computationally expensive process, right. So, yes, it is a computationally expensive process, and you can also see that in the damped Newton's method and modified Newton's method, we still have this so called computationally intensive process, either H inverse or h k plus lambda I the whole inverse, right. So, we have not escaped this computationally expensive process in these with these small modifications. Okay. So, how do we take care of this issue? We actually use something called as the quasi Newton method, okay, but that is a topic for next week. Okay. So, week 6 we will discuss about various quasi Newton methods. Okay. So, where you will actually not have the matrix inversion process. Okay. So, without matrix inversion process you are actually going to solve the optimization problem. Okay. So, but we will shift that to next week. This is being the last lecture of this week Newton's method. Okay. So, we will actually discuss some more properties of Newton's method. Okay. So, yeah. So, let me actually start with a particular problem, okay, where let so I will just write it as some more properties. So, let f of x 1 x 2 be so x 1 minus 2 the whole power 4 plus x 2 minus 3 the whole power 4. Okay. Just by looking at this you would have told me that the minimum of f occurs at 2 comma 3, right. So, let me try to solve this using Newton's method, where x 0 is 3 comma 4. Okay. So, let us try and check if we get something out of this particular example. Okay. So, I will just write this as Newton's method with higher order functions. Okay. Of course, we want to just experiment with Newton's method. So, I will remove all this damped and modified Newton's and everything. Okay. So, I just copied this, but I will remove L. Okay. So, now this is the Newton's method, and I will modify the code to accommodate this problem. x1 minus 2 the whole power 4 and x2 minus 3 the whole power 4. Okay. And yeah, so this will be 12 into x1 squared and this is 12 into x2 squared. Okay. So, we will, so the answer is 2 comma 3. So, we will start with 3 comma 4, okay, just to see what happens. Okay. Yeah, so I have written the values of grad and h slightly incorrect. Yeah, so this is the actual grad of x and h of x. So, let us, yeah. So, yeah, you can see that you got to the answer 2 comma 3. Yeah, there is a slight error 2.005 and 3.005, but that is because of 1 e minus 6. Okay. So, let me tell you, so it has I mean you might think that after seeing gradient descent and say conjugate gradient Fletcher-Reeves algorithm where it takes 30 or 40 steps and so on, 13 seems to be a smaller number, right, that is correct, but for Newton's method 13 is actually a high number. Okay. So, usually I mean you can see that many of the algorithms converge in a much smaller number of steps in single digits 4, 7, 6 and so on. If it is 13 it is actually on the higher side. Okay. So, yeah I mean that is just to indicate to you that 13 is not a small number. So, if it takes a little bit of I mean if it takes a little more iterations, we should try and figure out what the reason is, right. Okay. So, we will do that, but before that I will show you a few more things. One is, so let me actually increase this power. So, this is a fourth order equation, right, a quartic equation, right, or biquadratic equation, however you have learnt it from your high school. Okay. So, let us say I put the order of the function as 10. Okay. So, that is 10 into x naught minus 2 power 9 and 10 into x 1 minus 3 power 9, and this will be 90 into x naught minus 2 power 8 sorry, and 90 into x 1 minus 3 power 8. Okay. Yeah, so I can start with 3 comma 4. Let us see where this is going to take us. Okay. So, it has taken us to the answer in 16 steps, but you can see that the error is slightly large. That is also not because of the I mean the problem with the algorithm, it is because of I mean the tolerance that we have chosen. Okay. So, yeah, so even 0.15 power 9 the whole squared plus 0.15 power 9 the whole squared, the square root actually crosses 1 e minus 6, that is the reason. Okay. So, that is not the problem, but you can see that the number of iterations has increased. Okay. Now, let me increase this to 100. And this will be 9900, this is 98, and this is 9900 and this is 98. Okay. Let us see how many steps it takes. Okay. It has increased and you can see that the answer is 2.825 and 3.825. Okay. So, what I want to mention to you is somehow if the order of the Newton's method increases. Okay. So, instead of 2, 3, 4, if it increases to 10, 15, 20, 100, the number of steps it takes is usually on the higher side. Okay. So, it is not just a problem with Newton's method. I mean, so if you want me to do this for say Fletcher-Reeves, okay. So I will just do it for Fletcher-Reeves just to show you what might happen. Okay. Yeah. So yeah, I will just use this same algorithm or same code rather, and just change f of x and grad of x. Yeah, and I will also change this to 3, 4. Okay. I think something happened. Yeah, sorry. Yeah, and just let me do it with 4 to show you what is happening. Let us see. Yeah. So, you can see that Fletcher-Reeves actually takes 2649 iterations just to compute the answer for a quartic equation, right. And similarly, if I change it maybe to 6, so that I do not want to test your patience by making you wait for long. So, it has taken 9701. Okay. So, what is the moral of the story? It is that when you have, so I will just write down the yeah, the title. Yeah. So, when you have a higher order function where, I mean, higher order function alone is not a problem, but when you have multiple roots at the same point. Okay. So, like for example, x minus 1 the whole cube, x minus 7 the whole power 10. So, what does it mean? It means that there are 10 roots at the point 7 itself. Okay. So, when that happens, the algorithms that we are working on actually slows down. Okay. What is the reason? So, I will explain it both analytically and graphically. Okay. So, yeah, to explain it analytically. Okay. So, yeah, maybe I will take a simpler example. Let us say let f of x equal x minus a power n, yeah, where n is a positive integer. Okay. So, if you look at Newton's method, so yeah, let us say you start at some x naught, that is okay. So, you will have x 1 equals x 0 minus, okay. So, h inverse is f double dash, right. So, that is 1 by f double dash of x naught into grad of x, that is f dash of x naught, right. So, we can compute both of these very easily. So, this is n into x minus a power n minus 1, and this is n to n minus 1 into x minus a power x 0 actually power n minus 2, and that is equal to so this cancels and this cancels. So, you have x naught minus x naught minus a by n minus 1. Okay. So, to be precise, I mean I can simplify this as well, that is actually n minus 2 by n minus 1 into x naught minus or plus a by n minus 1. Okay. All right. So, let us again compute x 2 to just show you what actually happens. Okay. So, I mean the process would be the same, you can verify that. So, it would just be n minus 2 by n minus 1 into x 1 plus a by n minus 1. So, if you write this again, you will have n minus 2 by n minus 1 the whole squared x 0 plus a by n minus 1 into n minus 2 by n minus 1 plus 1. Okay. So, that is x 2. Now, yeah, so okay, I mean just to finish what is actually happening. So, x 3 is n minus 2 by n minus 1 x 2 plus a by n minus 1, which is n minus 2 by n minus 1 cube x 0 plus a by n minus 1 into n minus 2 by n minus 1 the whole squared plus n minus 2 by n minus 1 plus 1, right. So, in general x k will be n minus 2 by n minus 1 x 0, so I mean I am just repeating this, k power k x 0 plus a by n minus 1 into from k minus 1 to 1. So, you can see that this is a geometric progression, the sum of a geometric progression. So, that will be n minus 2 by n minus 1 power k x 0 plus a by n minus 1 into, so this will be 1 minus n minus 2 by n minus 1 power k by 1 minus n minus 2 by n minus 1, which is 1 by n minus 1. So, this and this cancels. So, you have n minus 2 by n minus 1 power k x naught plus a into 1 minus n minus 2 by n minus 1 power k. Okay. So, you can see that at least as k tends to infinity, this term goes to 0 because this is less than 1. This term also goes to 0. So, you converge to a, which is the right answer. Okay. But then what is the problem? The problem is that the convergence to a. Okay. So, I mean the first step it is a into 1 minus n minus 2 by n minus 1. In the next step it is a into 1 minus n minus 2 by n minus 1 the whole squared. In the third step it is a into 1 minus n minus 2 by n minus 1 the whole cube, and so on, right. What happens when n becomes large, when n becomes 10, n becomes 100, right. The movement towards a happens very slowly, right. So, it is like 1 minus x power k, where if x is low, the increase the rate of increase is very slow, right. So, that is the reason I mean when you actually increase the value of n, right. So, the convergence to a gets slower and slower and slower, and this is a phenomenon that actually occurs whenever you have multiple roots at a particular point. Okay. So, I mean this is like a weird issue that occurs, for example, in gradient descent you had this issue that if the eigenvalues of the Hessian matrix are far apart, the convergence becomes slow, right. In a similar way, the convergence becomes slow in of course in Newton's method, in other methods as well, when when you have multiple roots at a particular point. Okay. I will also explain this graphically. Okay. So, consider this curve. Okay. So, let us say it has multiple roots at the point A. Okay. So, let us say this is x minus a power n. So, suppose n is equal to 2. Okay. So, you will have a curve which looks like this, right. So, this is when n is equal to 2. So, suppose n is equal to 4 for instance, okay. The curve will look like this, right. I think I am not drawing it properly. Okay. Yeah. So, and suppose if you have say n equal to some say n equal to 10 or something. Okay. So, here it will be like let me choose another color. Yeah, it will be like, okay, it is completely invisible. Yeah, let us try this, this is better. So, as n increases, you can see that around A the curve actually becomes flat, it gets flatter and flatter and flatter and flatter and flatter, right. So, yeah, like almost parallel to x axis, right. So, if the curve is very flat, then I mean the inverse actually gets I mean it gets berserk, you can say, right, because I mean if you that is like having a second order derivative that is close to 0, right. So, H inverse I mean suffers from this issue. Okay. So, that I mean the issue is pronounced as n becomes higher and higher and higher. Okay. So, that is the reason why you actually have this kind of issues when you increase the value of n. So, as I said, this is an issue with I mean every method and Newton's method as well. Okay. But this is just a phenomenon that yeah, when you have multiple roots at a particular point, I mean it is good that you detect that particular thing rather than attempting to correct it with Newton's method or any other method. Okay. Fine, I mean I wanted to indicate this weird behavior before closing Newton's method. So, yeah, before ending this lecture, I will give an overview of what we have learnt this week. We started with the general form of Newton's algorithm, right, which is what you see here. You just choose dk to be minus hk inverse gk and alpha k to be 1, and that is it. So, it had many good properties that I mean for quadratic functions it just converged in one step, and even for the other functions it converges with an order of convergence equal to 2, that is quadratic order of convergence, while the earlier ones were linear order of convergence. But it also suffered from quite a bit of issues like no global convergence, and the direction that we take need not be descent direction, and yeah, matrix inversion could be a computationally expensive process, or we could actually end up with singular HK. We saw quite a few examples with that. We also showed that this Newton's method is locally convergent and the order of convergence is quadratic. Okay, that is the proof. and to get around these issues, for getting around the no global convergence property, we use the damped Newton's method, which is just choosing alpha k using backtracking line search, nothing fancy. That is Newton's method, but alpha k is not 1, but you choose alpha k by backtracking line search, and if h k is not positive definite, so that you get around by modified Newton's method, where instead of h k in minus h k inverse dk, you put minus h k plus lambda k I inverse dk. So, where lambda k was found from the eigenvalues of h k, the minimum eigenvalue of h k to be precise. So, that got around the issues of singular h k and minus h k inverse dk not being a descent direction. And finally, we have also discussed a property when f of x has multiple roots at a particular point. Okay. Yeah, I mean, so we saw examples where yeah, the convergence is slower, and that occurs basically because of the steep rise that you, I mean, the flat nature of the curve around A, that actually causes such problems when you have multiple roots at A, and it gets pronounced when the number of roots is higher and higher and higher. Okay. So, as a final comment, please recall that we are still stuck with one issue, which is the inversion of h at each step, which is actually a computationally expensive process, and that has to be done in every step, which is actually a pain. Okay. So, how do you get around it? You get around using quasi Newton methods, which is what we are going to see in the next lecture. Thank you.